there has been a lot of activity in the chat window and also on our own Slack window. These are related generally to two things. There's discussion about the orbital anisotropies in the analysis that Andrea presented, and then there's discussion about this lovely Green Valley stacked spectrum that Karen showed. I'm not gonna, I don't think I've pulled anything out of the chat that I necessarily want to raise here as a question, but I'm just gonna open it up now to anybody who would like to raise some topic for discussion or consideration. So if one of the things we obviously would like to do in Go Green is to write this great paper that solves all of galaxy formation by tying all these things together, and that proves challenging. We talked about that a little bit yesterday with trying to reconcile the shape of the stellar mass functions that REMCO is measuring with the ages of the quiescent galaxies and the star formation rates on the main sequence. And I think looking at these transition galaxies that Karen has presented is also a bit of a puzzle, because it depends, as we've said, a little bit how you count them. But I'm not sure that we're seeing a large and obvious population of post-starburst galaxies or things that are clearly transition galaxies in the cluster that aren't there in the field. And again, I think this depends a little bit how you ask the question, but just one interpretation is that what she is seeing is also a lack of a direct signature for lots of actively transforming galaxies in the cluster right now, which again points to the activity having happened much longer ago. That's at least a hypothesis that I think is partially consistent with a lot of what we see. Be interested to hear people's thoughts on that.
I mean, Adam, in his G-class papers, found that there was an excess of post-starburst, right? But that it stopped close to the center of the cluster, if I remember that correctly.
That's right.
So and those are slightly lower redshift than ours, right? So I think there were more of those at 0.8 or 0.9 than at 1.1. And so I'm just trying to understand, I hate the idea of there being any transition epochs, because the universe doesn't work in actually having transition epochs. Nobody gets to throw the global switch that makes that happen. So is it something physical that's happening where we don't see an excess of things that look like post-starbursts? Or do we just have to be really careful what we're calling a post-starburst versus the transition galaxy? I mean, Karen has 3 different definitions. The post-starburst fraction is low, but as Howard pointed out, there also seems to be this trend that increases as you go towards the center of the cluster. So I'm just trying to reconcile whether or not yeah, go ahead. I'm just trying to figure out whether or not what Adam saw in G-class is actually consistent with what we saw, or if there's a difference. I guess that's part of the question.
Yeah, and I think we still haven't fully answered that. I think and I think if I remember the numbers right, globally, the fraction of things Karen sees in the cluster is a little bit lower than what Adam finds in G-class, but statistically consistent. And what she finds in the field is a little bit higher than what Adam found in G-class. And so that the overall difference between what's in the cluster and the field is a smaller contrast. I think that's correct. So Karen's put up her slide. I don't know, do you want to say more about that, Karen?
Well, it's tricky because her outer cluster is below the field, right? So there's some variance in there that's not being captured by the internal uncertainties.
And this could come back, there was a question earlier about how the field is being defined, and the field is being defined from the outskirts regions of these clusters where, amongst other issues, we don't necessarily have a whole lot of area, right? We could do better by trying to do this self-consistently using all of UltraVista or something.
I mean, I always just like saying troubling statements to get under people's skin, but I found that there was a very strong dependence of post-starburst fraction on mass. It's much more commonly low mass galaxies than high mass galaxies. And so I would say that I wouldn't use a post-starburst fraction of everything because it really depends on, you know, the underlying sampling of the cluster. Does, you know, how many high mass galaxies does Go Green have relative to low mass galaxies? If just you've sampled more or less, you will change the fraction. It really kind of needs to be fraction at fixed mass, if you see what I'm saying. So I think I wouldn't interpret that too much until we, you know, but I think we know the spectroscopic sampling corrections, and so you could probably easily go backwards. It just has, it will increase the error bars. I think you just need to do the integral, right? I mean, I think of it sort of as like a sausage making, you know, the meat goes in to the grinder and the sausage comes out the other end. I mean, we know from simulations what's going in. We know from slightly lower redshift how many quenched galaxies there are. As long as you know how long the post-starburst phase lasts, you could figure out if it's consistent or not. I mean, to be honest with you, my concern of having 10% post-starburst fraction is that it's actually too high. You know, if the post-starburst fraction only lasts a few 100 million years, and that, you know, if you think about how quickly the quenched fraction changes with redshift, it might, I think we got something like 50% at redshift 1, and it goes to 70% at redshift a half. Well, there's there's many gigayears in there, and you've got a post-starburst fraction that only lasts for a few 100 million years. You're actually seeing way too many post-starburst galaxies. Anyway, it's an easy integral to do. You just need, you know, the sausage and the meat and the grinder, and you just do the integral, you know.
The time scale can be the difficult thing, but I absolutely agree. I think that what's clear about all these classifications is that they're certainly not going to be purely things that are transitioning one way from the blue sequence to the red sequence. There's a number of ways, and this is partly related to our discussion on the appearance of the stacked spectrum. There's a number of ways that you can get things in the green valley, or to have a post-starburst-like spectrum involving dust, involving rejuvenated quiescent galaxies that have a little merger or something, involving AGN. And so at best, you know, we would hope that these classifications would capture everything that is transitioning from blue to red, but there's undoubtedly other stuff in there as well, which is why the fractions look high. That complicates interpretation.
Yeah, it's interesting. So I couldn't resist, and I went back and read Bianca's paper in the last little while. And so I just want to say that I'm wrong. You can get that spectra very easily. And so I hear what you're saying, Bianca, and it is 10% of all galaxies in low redshift clusters. I'll only shoot back that if you go back to your paper, your claim is that most of them are probably ULIRGs that are dusty. And so if that's true, then that really complicates our Green Valley selection. You know, Michael, you're saying there's other things in the Green Valley. That really complicates this whole Green Valley thing, because if you're getting an average spectrum as an E plus A, E bracket A, and Bianca tells us that she thinks most of those are ULIRGs, that's certainly, that's not the Green Valley we're looking for.
Sorry, one step back. I'm not claiming that what the EA spectra we are seeing in distant clusters are ULIRGs. I'm saying that at low redshift, these spectra are found in ULIRGs. The ones in distant clusters, we had several studies also with Spitzer later of the distant clusters, and we saw that some of them were luminous infrared galaxies, but only some of them. So there is an excess of dust, but not all of them were really starburst in the sense. There is a nice paper from Dressler, which is later with the Spitzer. There's also Rike on that, I think. I can send you the references, where we showed that there is dust, there is star formation, but not all of these are luminous infrared galaxies or ULIRGs. No way. No way, they are not so extreme. That's not what I'm claiming.
Yeah, no, well, so I only have your original paper, and you're right. You claim the other can be post-starburst galaxies with residual star formation. And then some
no, but
are...
also, even those that are dusty, they are not they don't have star formation. We measure the star formation from Spitzer, you know, and they're not extreme. They're not like 100 solar masses per year, but they are star-forming galaxies, and they are very dusty. These two things combine, and the Wolf paper that somebody referred to is they found similar things, a low redshift, you know, 0.2, evidence for what they call dusty spirals. You know, it all came together. I'm not making a strong case. I'm just saying that that is a stacked spectrum. I would first look at separate that sample splitting with O2, without O2, just to check whether there is a, you know, when you stack a spectrum, you know, well, it can be that that is a typically post-Arbus, and then there are a couple of shooting things with O2, and you mix things up, and then the Balmer, you know, the photons and angstrom break is mixed up. So I would suggest—
I've done it many times.
Yeah, so I would suggest just dividing the two, also to check how many real post-Arbus there are. You know, if you take out those with oxygen 2 in emission, you might still be left with a population that where you see the Balmer line. Regarding the post-Arbus, the discussion, I just want to say I agree with what you guys are telling. The thing is, the fraction of post-Arbus, of course, will depend very strongly on how you identify them. Very strongly. So the absolute numbers don't make much sense, depending on the selection of those things.
Well, except that, but I think the issue here is that we're trying to do them exactly the same way Adam did. So that comparison should be fair.
Okay, you mean with Adam's results?
Right. I think there's, you know, and all points Adam made are right, but we haven't totally reconciled the G-class result with what we're finding in Go Green.
No, okay,
and there we're doing it the same way.
Yeah, that remains a puzzle. Yeah, I agree.
And there's also an issue with using O2 as a rejection step for identifying post-Arbus galaxies, because at these redshifts with lots of young stellar populations, you'll have a lot of post-AGB stars that are also heating the ISM. And so you can get weak O2 lines, and as Adam mentioned, AGN, that don't come from star formation. I mean, Renbin Yan's written about this at LOSI and lots of other people since then. And it's probably all those problems get worse at high Z, just because AGN activity is higher, the fraction of young populations is higher, the gas in the galaxy, that fraction's higher, so it can be heated more efficiently perhaps. So we have to think about how do we, when we identify post-Starbursts, are we throwing out lots of galaxies based on their O2 when they don't really actually have star formation?
So I'd like to just pause here a moment. We have the rest of the week internally, the Go Green team is meeting to discuss about lots of things. And so most of the conversation here has been between people at the Go Green team. I want to make sure we leave a bit of a gap for all our guests who've joined us for a couple of days to tell us about their thoughts, questions, or how their own data or observations perhaps relate to some of this discussion. I mean, we can keep talking, but we certainly know that works. But give a little window here if you'd like to say something.
Hi, sorry. This is V Tran. I've just been listening to some of the talks, and thanks a lot for organizing this. I've been enjoying catching up with the field. I did have one question, and I'm not sure if maybe I missed it because I was in and out a little bit. But have you guys looked, since you were doing this great SED modeling, I believe there's a talk yesterday on it, did you also try to match like the stellar and gas metallices? I mean, I know that there's some work, I know Adam, I think Muslin's been involved with this with Legacy, or I'm maybe making something up, I don't know. Or Adam, that's apparently something you're going to work on, I don't know either. But have you guys, since you do now have these different epochs between Go Green and then of course the lower redshift work, you can, in theory, build a self-consistent model in terms of maybe along the lines of the post-Starburst population, what they would evolve into, and how that would nominally increase the stellar metallicity enrichment, stuff like that. So I was just curious if anyone was working on that.
So we don't have gas phase metallicities because we have effectively only O2 emission. We do in principle have stellar metallicities. Christy talked a little bit about this in the discussion yesterday, and I'll turn it over to her when I address it again. The challenge there is that the metallicities we get are pretty sensitive to the prior we put on the STD fitting. We end up with results which do appear to break, the age metallicity dust degeneracy in the SED fits. But nonetheless, the priors and the model choices, for example, for the dust do influence that. So we are not yet, I would say, totally confident that the metallicities we're measuring, especially given the spectral range we have in terms of line coverage, are robust on their own. So we have not been looking into a project and directly comparing the metallicities because we're not sure of the extent to which we believe those in an absolute sense. Christy, I don't know if you'd like to add to anything I said.
No, I think that pretty much covers it. So yeah, the stellar metallicities are included in the fit with a prior for the mass metallicity relationship of the local field galaxies. But we're not totally confident that the posterior is recovered a result that's independent of the priors.
I'll just add, V, you're not making stuff up. The legacy team is working very hard on stellar metallicities, but they are, I'm kind of just watching peripherally, but it is an uphill battle to measure stellar metallicities. In a relative sense, I think as Christie's done, that's one thing, but the absolute stellar metallicity is a real pain. There's this feedback loop with the photometry, because it affects the dust, and you're kind of better off without the photometry at some level is what they're finding. But then continuum, relative flux calibration of the continuum and the spectra becomes absolutely paramount. And we know with slit losses, seeing, and Skytree, it's turning out to be a massive headache in legacy, and they have much better spectra than us. It's super hard.
Yeah, it's a good point. One thing that didn't come through in Christie's talk, but Christie spent a long time obviously trying to, it's always this nice idea to fit the spectra and the photometry together. And of course, one of the challenges that the spectra are rarely spectrophotometrically calibrated well enough. And you have a lot of pixels in the continuum, which drive your chi-squared of your fit. And so, there are parameters in the fitting that allows for effectively fitting out errors in the continuum calibration and other systematics associated with the spectra. We've tried to work really hard to get something robust out, but it's another factor that really influences the answer in the end, is how you treat the relative continuum of the spectrum and the photometry, and which one do you believe, and the differences we've seen between cluster and field are generally pretty robust to all these things. And so that's why I think, that result of the ages between cluster and field is robust, at least in a relative sense. But if we now want to take the actual metallicities of these galaxies and compare them to lower redshift, that's harder work. Kate Rowlands has noted in chat, it would be good to split the post-starburst galaxies by stellar mass and the field, and yes, and we have done that. I think Karen's got plots somewhere on post-starburst broken down by mass that we've simplified for this presentation. But absolutely agree that these things depend quite strongly on stellar mass. I mean, again, that this isn't new here, but as we've seen for a long time, a lot of these, the quenching mechanisms and transition mechanisms are all very strongly stellar mass dependent. So unless you control for that and you take out that correlation, you have to be very careful about the comparisons. Sean McGee reminds us this on every telecon, not to present numbers for the whole population, but make sure we do it as a function of stellar mass, because they're all very dependent.
Michael, I'd like to follow up on this discussion about the stellar populations. This is Joel Roediger again from NRC. So the statement that that you and Christy have made is that the posteriors you get on the stellar metallicities, you're not convinced that they reflect new constraints from the data, that they look really similar to the priors. Then are you not concerned that the prior you're making on the stellar metallicities isn't biasing your stellar ages too much by virtue of the age metallicity degeneracy.
I think it. Sorry, Christy, you should answer.
My Wi-Fi dropped, so I'm not sure if I heard the first part of that conversation. It was on the priors of the
basically,
master
I'm just asking the question that because of the age metallicity degeneracy, by placing a prior that you claim is by placing a prior on the stellar metallicity that you claim has a strong effect on your conclusions about the stellar metallicity, then how do you know your stellar ages aren't likewise being affected?
So we originally did the fitting without using a joint prior on the mass metallicity. We just left it as a uniform prior. And the age difference between the field and cluster galaxies was virtually unchanged. So the major conclusion of the work was unchanged, but the metallicities tended to be a little bit lower, even in that case, which was our motivation for something is weird. Let's see how the prior affects what the metallicities are doing and how that'll affect the result. So as far as that goes, the result of our work doesn't change, but we know that the prior is doing something to significantly affect the metallicities. Does that answer your question?
If I can expand on that a little bit, I think what, if our metallicities are a little bit low, I'm not 100% convinced that's true, but if they're a little bit lower than they should be, that means our ages are a little bit older than they should be. And again, compared to some literature, our galaxies might look a bit older than you'd find in other studies. And again, as Christy said, what we first did was running without that prior. Our galaxies were really quite old and low metallicity. The age difference between cluster and field has remained robust, but what that absolute age is does float around depending on what we do with that mass metallicity prior. So I think, it's the same as people have been saying for years in this game. You've got to take the absolute values of both ages and metallicities with a grain of salt, and relative ages can be interpreted a little more, a little better.
Okay, thank you.
Maybe just because I have to leave probably rather soon. Just from a simulation side, because we have been discussing already about this. So what we did is we used our simulation and used the same criterion that Adam has been using for his paper in 2014 to classify the PSBs in the galaxy clusters. And actually we find them to live exactly from the simulations where Adam also found them to be. So the population seemed to match rather nicely. So we traced them, how they were formed. And about 1/3 is made by mergers. The rest is made by the cluster environment with a similar mass trend that Adam has been finding. And the interesting thing for us is that this is very different from what we find for the PSBs in the fields, where most of them are actually made by the mergers. So these populations, at least from the simulations, seem to be rather different. Now, this is not a simulation that was included in Egidius' work. It's from the Magneticum simulation. So I have to admit, we haven't checked all the things that Egidius has been showing, but we have been looking at the clusters quite extensively, and the boxes are much larger than what has been discussed before. So it's actually suited for this. So I'm not saying the simulations are perfectly right here, but I think it's an interesting thing to see that these populations are diverging rather nicely from each other between field and clusters. So we hope to have this out this year. It's again a paper by lots, so maybe once we are done with preparing this, you might find this interesting, and would be very interesting to see what happens if we actually compare to what is found for GOO-GREEN, because it's even higher redshifts, and we know that if we go to farther redshifts like that equals 2 and 3, we are getting worse and worse with matching the observations. So it would be really nice to see when this getting worse really becomes important, because for understanding why things don't fit, probably the high redshifts are the key. So the more data we get to compare there, the better it is also for us to understand why the models don't work. So
Great,
I'm
thank
looking forward to see your PSPs at some point so we can actually use them as well.
Great.
That's super cool. Can I make a quick comment, which is, have you looked at the sizes and morphologies of the post-starburst galaxies in the simulation?
So yes and no. The problem is, as I said, and that's probably me being conservative, I don't trust galaxies with less than 1,000 particles because I'm a galaxy person. Normally I don't do clusters, so that's me being skeptical. If I ignore me being skeptical, they look nice.
Yeah, well, one thing that's interesting is Jasleen Matheru did the mass size relation of post-starbursts and clusters. I actually showed it yesterday, and they're big and fluffy. And then the legacy team has done that. There's a paper by Po-Feng Wu, and all the post-starbursts in the field are super nuggety and small. The sizes between the cluster post-starbursts and the field post-starbursts are like, there's no overlap at all. They're totally different objects. And for a while we argued about this, and then we came to the conclusion that it must be different processes, like ram pressure strip ring creates post-starbursts in the field and mergers create post-starbursts in, ram pressure stripping in the cluster, mergers in the field, and the evidence being that the morphologies are nothing alike. So I think it's really interesting that actually you're coming to the same conclusion with the simulation, and maybe using the sizes you can reconcile Po-Feng stuff with Jasleen stuff.
Did you publish that? Because I didn't find that when I went through the literature.
There's a Matheru 2020, just came out a few months ago for the clusters, and Wu is also 2020, just came out for legacy. It's WU, and his first name is Po-Feng.
Okay.
And so they're totally opposite results, and I'm on both papers, and they're arguing with each other, and I'm like, I don't know how to deal with this, but different processes could maybe solve the problem.
Exactly. So that's nice to see that this is seen in the observations, because it had us struggle quite a lot because we were worried that we find different processes to be dominant, but it's great to see that you find that too. So we are not that wrong.
Well, we find different sizes, so we argue it's different processes, but we don't know. It's you know, circumstantial. Anyway, fun to hear.
Great, thanks. I see that Rowan Hagar's had your hand up for a while. I'm sorry, I missed it in the window.
Yeah, no, that's fine. Thanks. It's actually kind of related to what we were just talking about. Although I have just realised that my question's been somewhat answered in the chat, but I'll mention it anyway. I was a little concerned about the in Egidius's talk, the use of the Bahamas and Maxis galaxies down to masses of about 10 to the 10 solar masses, given the resolution's only about 10 to the 9. Looking at properties of galaxies of the order of 10 particles in them seems a little bit dangerous to me, and I wondered whether that was whether that was kind of a valid choice, whether you can trust properties of galaxies down to that low mass.
Yes, it's a perfectly valid concern, and you need to keep that in mind, that yes, 10 particles isn't much, but at least the star formation rates look okay when measured down to 10 to the 10. I guess that's all I can say. That the particles at least have the correct star formation rates, as shown by observations.
Yeah.
Certainly not go any lower than that. That's already pushing it, and that's what limited my selection out to 10 to the 10.
Yeah, I mean, I think it would be interesting. I think there's probably other simulations that would be interesting to compare the Go Green results to. I mean, yeah, for example, so I'm involved with the 300 project, which is a set of simulations that it's a similar number of clusters to Maxis, but with a higher resolution. I think you could probably get a lot more than 10 particles per galaxy down at that mass of those simulations. I think it'd be interesting to look at how Go Green compares to them, and they might have slightly more trustworthy galaxy properties.
Oh yeah, absolutely.
I mean, just to add to this, because we looked into the resolution issue for our simulations, of course, as well. And the biggest issue is the gas. It's not so much the star formation rate, but if you throw something into a cluster with that few particles, the stripping processes behave very different from when you have really many particles. So my worry would not be so much the star formation rate, but especially what happens to the stripping processes, and that changes quite strongly the appearances of the galaxies. So in that sense, like I said, I'm probably very conservative in my 1,000 particles at least rule, but from the testings I did, this was what I found to be trustworthy as a lower limit, because everything below, when we did the same simulations with same object, different resolutions, you could see that there was just this problem, especially with the environment kicking in rather strongly.
Mm-hmm.
And presumably that's going to particularly affect the quenching of these galaxies, particularly down those low masses as well. So I'd be very skeptical of the quench fractions of that kind of mass range using these simulations as opposed to some with higher resolution.
Right. Now that I think about it, that may be the reason why low mass galaxies in Bahamas just get quenched immediately, which may have something to do with gas, which I don't believe has been tested in detail.
Yeah, sorry, we didn't publish it yet. Sorry, we are always crappy with publishing. I know that. Sorry.
Yeah, I think related to that, something clearly an element. We talked about quenching of galaxies as they're in clusters, but disruption of galaxies is also something that can dramatically transform the population. You can misinterpret evolution in quenched fractions, for example, which are actually due to disruption, especially of low mass galaxies. So that's, could be something that happens in the real universe. And of course, in the simulations, then you have both the real effect, but when you're using galaxies with a small number of particles, you'll be artificially disrupting, presumably, galaxies that you wouldn't be in the simulation. So what might be interpreted as a difference in quenching mechanisms or different effectiveness of quenching is actually due to disrupting the wrong types of galaxies at the wrong times. And I think it's something, of course, we have to really worry about and think about when we compare. Again, one of the next big steps for Go Green is doing a careful comparison of the high redshift clusters to clusters at lower redshift and trying to connect them all. And of course, worrying about what happens to galaxies both disrupting and merging between those two epochs can have a big impact on that interpretation. Okay, we still have a few minutes left. Other comments or questions?
Hi, this is Lisa again. Can I ask a more technical question? And I keep asking this at every talk, but Jasline's results seem very interesting. And I was just wondering how are sizes of galaxies computed? I guess I could explain. I'm coming at this from a very morphology-based background. And one of the things that we worry about a lot is what data is being used and what's the signal to noise of the images you use to compute morphology. So I remember in one of the talks someone mentioned the HST imaging of signal to noise 1.5 per pixel. And I was wondering if those are the images used for like more of the morphological work.
Adam, this is for you, I think.
Well, yeah, I guess I was checking if Jasleen was here because she was here yesterday, but I guess she's not. Can't remember, I have to look at it, but we know that basically you can't get anything reliable below a signal to noise of about 30 per galaxy. So it's basically cut off at that limit. And if you look at her paper, there's a million simulations that, not a million. There are simulations that compare the sizes to 3D HST and how that's done. And so it's very, very carefully matched to the 3D HST sizes and reproduces those very well so that we get a fair comparison between cluster and field.
Okay, thank you. Yeah, I'll look at the more recent papers. I've looked at some of Jasline's papers before, and the work you guys do is very, very cool. And I'm trying to reconcile in my mind, why do I find that these cluster galaxies are more compact and you guys find cluster galaxies to be less compact? So yeah, this is something I will look at in more detail. But also with the discussion that was happening before, in our work, we find that they are more compact. And I completely agree with what people have said before about like the importance of physical processes that happen in clusters that simulations may not model well on these really compact objects that I'm looking at. For example, tidal interactions and things like that, not just ramp pressure stripping.
Well, sorry, just to be clear, Jasleen finds that they are more compact in clusters. They're smaller by 25%. Is that not what you find? You said
sorry, I was talking about, yeah, keep going.
No, we find that they are more compact in clusters. It's not a lot. It's only, you know, 0.1 dex, 25%, but they are more compact in clusters. So you said you also find they're more compact.
Yeah, ours are significantly more compact, so I think it's a bigger difference. But I thought you said that the post-starbursts are more extended.
Ah, okay, I see. So sorry, it's a confusion. So quiescent galaxies on average are more compact. Also star-forming galaxies are more compact, but the post-starburst galaxies are kind of halfway in between the two, is what Jasleen finds. Whereas if you go to the field, post-starburst galaxies are actually smaller than the average quiescent galaxy, whereas in the cluster, they're in between the star-forming and quiescent galaxies. But on average, our quiescent and star-forming galaxies are 25% smaller than field galaxies of similar mass.
Yeah, that's really cool. And do you then think that the post-starburst becomes the compact quiescent galaxy with disk fading? Or like, what's the physical process there? I'm just wondering.
You can check out the paper. about 75% of the paper is trying to make that argument. What she found very clearly is that pure disk fading is not enough. If you just purely fade a disk, there's no way to do it. What you need is the disk to fade inside out, basically, to sort of, if you think this, you know, star formation makes it brighter. And so in order to go from a big disk to sort of compact nugget, you need to sort of keep some star formation in the center to keep it bright in the middle to make it all work out. And that's the only way that it works. It can't work from just taking the disk and making it fainter over time. But there's like 10 pages of that argument at the back of the paper. We really struggled to make it all work, which is kind of interesting in its own right.
Yeah, that's really cool. We were thinking a lot about like tidal interactions actually driving the gas inwards. So maybe a combination of those two things could lead to like a blue core that still has in-streaming gas while something else is removing the gas from the disk.
Yeah, it's a great thought. We should talk about it sometime.
That's great. We're just about at the top of the hour and the end of the public portion of this meeting. Last opportunity for a question or comment from somebody who hasn't had a chance to speak. Okay, then, you know, once again, I'd like to thank everybody for joining. It was great to see this turnout. Please do, if you're interested, please play with the data. I've had a little look at what the Data Labs presentation looks like, and this is really cool. I think this is a great, the idea of what the Data Labs is doing is to use GoGreen as a pilot project for hosting all LLP data from Gemini in the future. They were really efficient at putting this together, and it's nice. You don't have to download the data. We have Jupyter notebooks on there. You can just start playing with it yourself. And so I hope this inspires you a little bit to go and have a look at the data and use it and compare with your own work. And I hope you find it useful. Thanks once again to Donna Hayes from the Waterloo Center of Astrophysics for helping set this meeting up, and the whole meeting runs smoothly. And thanks to all the large team of GoGreen people. I've been involved in a lot of collaborations over the years, and I think this is hands down my favorite collaboration of all time. Everybody is engaged and active. You know, you often have these collaborations where there's 30 people, but one person does all the work, and that has been demonstrably not true in this collaboration. There has been a large team of people who've all taken on a large share of the work, and it couldn't have happened without any of them and all of them participating. So huge thank you to everybody for 5 years of effort to get us to this point. And thanks again to all of you for joining us today.
And I have to say, thanks to Michael for doing an amazing job leading this collaboration. I mean, Michael is very modest in saying that there's not one person doing a huge amount of work, but actually Michael did an incredibly large amount of work and also was incredibly effective as a leader of the collaboration. So he pulled us through the 5 years. So
Oh, you're
thank
so sweet, Greg. You're so sweet. Thank you.
I expect the delivery of the case of whiskey later.
Yeah, right. Okay, well, we can all break now for lunch or dinner or breakfast, depending on where you live, or midnight snack for some of you. And the rest of us, Go Green, will get together in half an hour to talk about things more in progress.